Hi, I want to talk about the three types of radioactive decay particles. They got their name based off the order in which they were discovered, and they're called alpha particles, beta particles, and gamma particles, because alpha, beta, and gamma are the first three letters of the Greek alphabet. Now, an alpha particle is the nucleus of a helium atom, so it has 2 protons and 2 neutrons. Beta particles, there are 3 of them, and the first beta particle to be discovered was electron release. And it's electron release from the nucleus of an atom. It has a reverse. You can capture electrons, and nuclear reactions, you could bombard alpha particles on an object, and you can have alpha particle capture as well as being a reverse process. One of the weird things, though, with beta radiation is sometimes there were observed particle decay events where the particles released had the exact same mass as an electron. They appeared to have the exact same size, exact same everything as an electron, except they happened to be positive. And it behaved as if there was just a positive electron. So those other types of particles, what are called beta plus particles, were named positrons. And the third class of radioactive particle are gamma particles, which are photons, just electromagnetic radiation given off. So let's talk about all 3 of those processes. So if you lose a helium nucleus from your atom, for example, U-238, U-238 will undergo alpha decay, and you would subtract off 4 nucleons, so the new particle would have 234 things in the nucleus. You've lost 2 protons, so that means you're left with 90 protons, and 90 protons is thorium-234 plus a helium nucleus. So one of the reasons why looking for deposits of helium is kind of a big deal. Helium generated on Earth is only generated through radioactive alpha decay. So if you are finding alpha sources, you're finding helium, and helium is able to escape Earth's atmosphere. So it's a not really renewable resource. So we would have to wait for more radioactive decay to happen, which usually happens over a very, very, very long period of time to keep generating more helium on Earth. Now for helium capture, if you bombard normal nitrogen, nitrogen-14, with alpha particles, then you end up getting oxygen-17, and you end up having a leftover proton. So 2 of the neutrons, 1 of the protons joins up with the nitrogen to make oxygen, and you have a hydrogen nucleus kind of hanging out on its own. Now with beta particles, carbon-14's form of radioactive decay is with beta minus emission. So what will happen is the carbon-14 nucleus will give off an electron. Well, if you remove a negative charge, one of those neutrons turns into a proton. So you still have 14 things in the nucleus, it's just 7 of them are now protons instead of 8 of them being neutrons and 6 being protons. So that means you now have nitrogen. And you have electrons. You also end up generating an antineutrino. And neutrinos were small, they're electrically neutral, they travel incredibly quickly, they very, very, very rarely react with matter, so it took a long time for neutrinos to be observed in a lab. It's just noticed that there would have to be a little bit of something extra to obey all of the conservation rules in that nuclear reaction that would show up. Now, similarly, electron capture involves neutrinos. So if you were to have a beryllium-7 isotope, and it were to capture an electron in its nucleus, Well, that electron joins up with a proton, becoming a neutron, so you still have 7 things in the nucleus. 3 of them are now protons, so you have lithium-7, and you need to release a regular neutron rather than an anti-neutron to make everything work out. Now the weird thing, positrons were actually the first type of antimatter to be discovered. An anti-neutron is the exact opposite of a neutron. It has the same mass, same properties, except its charge numbers end up getting flipped. And if an anti-neutron and a neutron were to meet up, they would annihilate each other, releasing the energy that's equal to their mass. Same thing with a positron and an electron. A positron and an electron get together, they eliminate themselves, and we get at least a couple of photons released. So sometimes folks talk about positronic technology. Well, if you're trying to build a positronic computer with positrons and ordinary matter, you have a giant antimatter-matter explosion on your hands. So that's an example of what's known as technobabble in science. So positrons are real particles. PET scans, positron emission tomography, are done by injecting positron sources. So one positron source is oxygen-15. Oxygen-15 will release a positron, so you end up subtracting a positive charge, a proton turns into a neutron, you still have 15 things in the nucleus, but you now have 7 protons instead of 8, so you've gone from oxygen to nitrogen, you release a positron, and you release a neutrino. So with positron emission tomography, you bind positron sources, beta plus decay sources, as parts of molecules that you want a particular thing that you want to image. So say cancer cells. Cancer cells love glucose. Stick that positron marker on that glucose atom. The cancer cells eat up that glucose. So if you see a source of photons being emitted from positron-electron annihilation in a point, that gives you a way of imaging where those cancer cells may be. Now, the last type of radiation or radioactive decay is radiation. It's the release of a photon from the nucleus. And cobalt-60 is an example of a gamma source. So cobalt-60 nuclei can end up in an energetic state, and nothing changes about the nucleus other than its internal energy. It drops to a lower energy state, releasing what tends to be very high frequency, which means very high energy light. That very high frequency has short wavelengths, which means those light waves can penetrate even very, very dense material. So it's hard to screen for. It tends to be at high energy, so when it does interact with material, it can be particularly damaging. Thanks for watching.